Good morning to everyone. Today's class I am going to discuss about MOS transistor, that is a figure of merit, and MOS transistor transconductance, output conductance, MOS transistor, and that is Nmos inverter. How the Nmos inverter is going to be constructed, how it is going to be performed based on the input conditions. Okay. And previous class we have discussed that is a relationship between IDS versus VDS. There we are discussed two concepts such as one is saturation, other one is non-saturation mode. So based on those two condition, we derive the equation, that is current equation IDS, by applying the voltages VDS and VGS. So some of the points we can use from that relationship here also for the implementation of transconductance, output conductance, and figure of merit. Okay. So these are the contents. These are the contents I am going to discuss here. That is MOS transistor transconductance GM and output conductance GDS. MOS transistor, that is a figure of merit, that is represented with the omega naught, that is a frequency component, and the pass transistor. So here just pass the transition, nothing but pass the logic level from one point to another point. And Nmos inverter. The inverter is implemented by using Nmos here. So how it is going to be working? By using the construction of Nmos transistor for the implementation of inverter, right? So the first case here, MOS transistor transconductance and output conductance, that is GDS, right? So here the transconductance is nothing but GM. So here it is GM represented with the GM here. That is the ratio of change in IDS and change in with respect to change in VGS, yet VDS is constant, nothing but transconductance, right? So let us see the point here. The transconductance expresses the relationship between output current IDS and the input voltage VGS, defined as the transconductance GM. Okay, you know that IDS nothing but drain to source current, that is change in current, and similarly change in voltage, that is applied voltage at gate with respect to source, that is VGS. And here it is VDS, nothing but applied drain voltage with respect to source or substrate, right? Now we want to find the expression for GM, that is nothing but transconductance. So you know these parameters, charge, nothing but it is represented with the QC, and drain to source current, that is IDS. It is tau, nothing but transition velocity or transition time, that is represented with the tau. Okay, so where tau is the nothing but it is transition time. Now we need to be calculate transconductance, then change in charge, nothing but also change in current. So that based on by using this equation here, if delta QC, that nothing but change in charge, and then it is equal to also change in current. So from this equation it can be modified as, that is change in current, delta IDS equal to delta QC by tau, right, from this equation, right? So but we know that transition time equal to L square by mu VDS. This is from in previous class, that is a relationship between IDS versus VDS, that is transition time in between source to drain to source. Okay, so now you can substitute this value in above equation, that is change in current, right? Change in current, that is here, this is the change in current, delta IDS equal to delta QC by tau. You can substitute the transition time value instead of this, right? So this is the transition time here. So that substitute this value in this change in current equation. So that is delta IDS equal to delta QC by L square by mu VDS, right? But from that, delta IDS equal to delta QC mu VDS by L square. So here mu is nothing but mobility of the charge carriers. but we know that charge equal to C into V, right? So here V nothing but voltage, here C nothing but gate capacitance, here Q nothing but charge. So here the charge is induced with this voltage. If the voltage changes, then automatically the charge is also changed. So here we can represent this equation in terms of change in charge. So nothing but delta QC equal to CG into delta VGS, right? So here if voltage will be changes, then charge is also changes because of by applying this gate voltage that will be induced charge in the channel between source and drain, right? So change in charge equal to that is gate capacitance into change in gate voltage with respect to source, right? Now you can substitute this value, this delta QC value in this equation, right? Now delta IDS equal to CG delta VGS mu into VDS by L square. Okay, so here the delta VGS you can transfer this value at left side as a denominator. Then therefore GM equal to transconductance equal to delta IDS by delta VGS, right? Delta IDS by delta VGS, that is equal to CG gate capacitance, mobility of the charge carriers, and drain to source voltage by length square of the channel. Okay, square of the channel length, right? So you know here the transconductor nothing but the ratio of change in drain to source voltage. See here the transconductor nothing but ratio of change in drain to source voltage with respect to change in gate to source voltage, right? So here delta IDS by delta VGS nothing but this is the value here, CG into mu VDS by L square, that is nothing but GM, right? But in saturation mode, VDS is equal to VGS minus VT. In saturation mode, VDS equal to VGS minus VT. So this thing is also taken from the previous class, that is relationship between IDS versus VDS. Because in saturation mode, VDS is equal to VGS minus VT. In non-saturation mode, VDS is less than VGS minus VT. Whereas in saturation, in this case, like, so you can substitute VDS value in above equation instead of VDS, right? So here, instead of VDS, you can substitute this saturation mode value. Then GM equal transconductance equal to CG mu by L square into VGS minus VT. But we know that the gate capacitance value when it is in parallel plates, we know that CG, that is nothing but gate capacitance, that is epsilon naught, epsilon insulation, and area of the channel by thickness of the channel here. So thickness of the dioxide layer, right? So substitute this CG value in above equation. Substitute this value in this equation, right? Then GM equal to mu epsilon insulation epsilon naught by D into W by L into VGS minus VT, right? So here this equation then form it as like this when we want to substitute this gate capacitance value in transconductance equation, right? The alternative way we can write this equation. So here let us see the complete form. Here it is nothing but beta. How it is going to be beta here? Firstly, K equal to mu epsilon insulation and epsilon naught by D. Okay, and here K into W by L, that is nothing but beta. So these parameters are taken from the IDS versus VDS relationship. Okay, so alternatively we can write the transconductance equation is GM equal beta into VGS minus VT. So this is the equation for transconductance of MOS transistors, right? Next, from the above expression, transconductance, it reveals the transconductance of the MOS transistor by increasing that can be MOS transistor can be increased by increasing the width of the channel. Okay, and increase its input capacitance and area occupied. So based on these things here, the transconductance is going to be increased, right? Next, the output conductance GDS can be expressed as, it is very simple, GDS equal to delta IDS by delta VGS. Okay, it is very simple. Output conductance, that is GDS, equal to delta IDS by delta VGS, that is equal to lambda into IDS. Where, so this parameter is here we can consider it as a only for simplification point of view. That's it. So lambda dot IDS, right? That is equal to 1 by L square, 1 by L whole square actually. But here the lambda is inversely proportional to 1 by L, and same thing IDS also inversely proportional to 1 by L, right? So then lambda into IDS is inversely proportional to 1 by L whole square, right? So here the output conductance value can be depending upon this inversely depending upon the channel length, right? So let us see here, the MOS transistor output conductance completely depends upon the channel length, right? So this is the channel length. L means nothing but it is the channel length. So the output conductance of MOS transistor completely depending upon the channel length, right? This is the transconductance of the MOS transistor and output conductance of the MOS transistor, right? Next, figure of merit. So here the omega nothing but it is a frequency component. You know all, it is a frequency component. Okay. The figure of merit omega naught is measure of frequency response and switching performance of the MOS transistor. It is the frequency response and switching performance of the MOS transistor, nothing but figure of merit here. So omega, which given as omega naught equal to Gm by Cg. Gm nothing but transconductance, C nothing but gate capacitance. You know the value Gm and Cg. So Gm is nothing but mu epsilon insulation epsilon naught by D into omega by W by L into VGS minus VT. Similarly, parallel plates gate capacitance value is epsilon insulation epsilon naught into area of the channel by thickness of the oxide. You can substitute these values in above equation, that is omega naught equal to Gm by Cg. So from that, after simplification, we are getting this value. So omega naught equal to Gm by Cg equal to mu by L square into VGS minus VT. That is equal to 1 by tau St. Right? So let us see here. Suppose we want to replace VGS minus VT. It is VDS, that is equal to VDS. Suppose in saturation mode. So here mu by L square into VGS minus VT, that is VGS minus it is VDS. So that is, let us take here tau Sd equal to L square by mu VDS. So here VDS, simply you can substitute this VDS equal to VGS minus VT. So then simply get this formation, right? Okay, so from this point here mu into VGS minus VT by L square nothing but that is 1 by tau St. 1 by tau St. So therefore omega naught equal to 1 by tau St. Since tau Sd equal to L square by mu VDS, right? So it shows the switching speed depends on the gate voltage. The switching speed depending on the gate voltage, that is above threshold. Carrier mobility and inversely square on the channel length. Inversely square of channel length. This is nothing but figure of merit, right? Next, pass transistor. Just pass means just pass the information from one point to another point. So here let us see here, A is the one MOS transistor, B is another MOS transistor, C is the another MOS transistor. Here these are the three devices here we are making to here connected as a series formation. Now we can apply these values. Then here initially it is a VDD, here it is point is X here, A, B, C are the inputs here. Okay, here let us see the point here. Unlike a bipolar transistor, the isolated nature of the gate allows MOS transistor, right? Here the isolation is available here, but it is a capacitive plates. Okay, the isolated nature of the gate allows MOS transistor to be used as switch. If here we can apply it is 1. Suppose it is going to be A is going to be 1, then the MOS transistor going to be here A transistor is going to be on. Suppose here it is 0, then A transistor is going to be off. So simply it acts as a switch, off, on, like that, right? So in series with a line carrying a logic levels, in a way that is similar to the use of relay contacts, similar to the use of relaying contact. So the relaying contact thing, there is a different levels. That level will be going to be carrying one step to like that, right? Here, so this application here, the application of the MOS device is called as a pass transistor. One of the application of this MOS transistor nothing but pass transistor, and switching logic array can be formed. For example, an AND array, as in figure AND array. So this is nothing but AND array, right? How it is going to be AND array? Because of here x equal to a dot b dot c. A dot b dot c nothing but it is going to be product operation. Okay, the product operation means it is AND array. AND means it is the AND gate means they perform the product operation. That performs the product operation. That's why a dot b dot c nothing but AND operation, AND array, right? So here x equal to a dot b dot c, that is logic 1, that is equal to VDD minus VT. Suppose here a equal to 1, b equal to 1 and c equal to 1. So and a equal to 1 here, then x is equal to VDD minus VT, right? So this is the response here. Okay, if a equal to 1, b equal to 1, c equal to 1, then this response, logic high response, will be carrying at x equal to VDD minus VT. So here VT nothing but threshold voltage. So here if you are applying voltage here a equal to 1, that drops VT because of the gate voltage is, if the gate voltage is greater than the threshold voltage, then only the device is going to be conducting mode. So in that way, VDD, V input is VGS minus VT, VGS minus VT. So some amount of voltage is lost at this particular transistor. That's why here x equal to VDD minus VT. The threshold voltage will be lost because of here V input is greater than the VT. Then only the device is going to be conducting mode. Now, right? Next. So here, let us point one more note is given. He is given there. Here means so that x assumes ground potential when a plus b plus c equal to 0. Okay, so this is a pass transistor. Next, NMOS inverter. Simply, as I told you in a first slide, NMOS inverter. The NMOS inverter here, the inverter is implemented by using NMOS inverters only, right? He can use here one is NMOS transistor, in other case other device nothing but resistor, and then you can implement the inverter operation. But some cases, some of the area where as in fabrication point the resistor is occupies very much more area, even at modest values. Even at modest values of resistor, it occupies very large area in fabrication point, in the form of in view of fabrication technique to design the NMOS inverter. So that is the drawback. Instead of that, we can use one more device here, nothing but that is depletion mode. Okay, let us see the diagram firstly. So this is the diagram here. This is the NMOS inverter circuit diagram. This is the here the one transistor here. Here is another transistor, MOS transistor here. It is the depletion mode device because of here it is a thick line. Apparently nothing but it is a NMOS depletion mode. Here the source is connected to the gate is connected to the here. Then for this connection, the device is always in on condition, right? And here it is NMOS transistor, enhancement mode transistor. Here the input is at gate. The output is taken to the drain of enhancement mode transistor. Okay, and here one other terminal is connected to the VDD here, and the source of this enhancement mode transistor is connected to the ground. But instead of this, and previous generally he can use one resistor here. He can use one resistor like this, okay, like this. But in this case, In this case, it is also performing inverter operation, but whereas going to be in chip designing process in fabrication technique, so it occupies very large area. But our aim is to reduce the area for the chip designing process by using VLSI technology. So instead of that, he can remove these resistor. Instead of this resistor, he can use depletion mode device, right? Right. Let us discuss all those things here. Right. At the first point here, a basic requirement for producing a complete range of logic circuit is the inverter. Right. A basic requirement for producing a complete range of logic. Complete range of logic means if you are applying input is 0, then it is getting output is 1. If you are applying input is 1, then it is going to be output as 0, like that. Okay, so this is needed for the restoring logic levels for NAND and NOR gate also. So the same thing here also we can implement a NAND and NOR gate by using NMOS inverter logic. We can implement NAND and NOR gate is also by using NMOS inverter logic. Okay, and for sequential and memory circuit of various forms, right? In the second case, the basic inverter circuit requires a transistor with a source connected to ground and load resistor of some sort connected to the form of drain to the power supply rail VDD. So this output is taken from the drain and the input applied between the gate and ground, right? That is VGS. If the the load resistor is connected to the power supply and source is connected to the output, drain is connected to the output and source is connected to the ground, and applied input is VGS, that is in between gate to source, that is also performing the inverter operation. But whereas in application techniques, even at modest value, it occupies very large area. So for that we can use, instead of load resistor, that is another device, that is nothing but depletion mode transistor, right? So here the resistors are conveniently produced on silicon substrate. Even at modest values occupies excessively large area, so that some other form of load resistance is required. A convenient way to solve this problem is to use a depletion mode transistor as the load, right? So coming to here, for the depletion mode transistor, the gate is connected to the source, so it is always on, right? In this configuration, the depletion mode device is called also pull up. From this onwards, we can say depletion mode is pull up and enhancement mode is pull down. So remember these words, okay? The depletion mode device is pull up device. The enhancement mode device is pull down device, right? So now it is called as pull up, PU, and here it is called as pull down, PD. Pull up and pull down. The enhancement mode device called as pull down, nothing but PD. So let us observe the point here. The inverter transfer the characteristics, we superimpose VGS equal 0, the depletion mode characteristics curve on the curve for the enhancement mode device. Okay, that maximum voltage across the enhancement mode device corresponding to minimum voltage across this depletion mode transistor. So the meaning of this point here, it is here the depletion mode is always on. Even here VGS equal 0, output is high. Here V input is 0, output is high. So by increasing this value, the current will be, there is a path in between VDD and VSS. The flow of current like this, okay, output current is going to be drop. Let us see the waveform here. So here maximum VDS, V input is 0, here, the maximum input is IDS is 0. So at VGS is 0, so this is the curve formation of this depletion mode transistor. Okay, so whereas At enhancement mode is 0.2 VDD and VGS equal 0.4 VDD and VGS is 0.5 VDD and VGS equal 0.5 0.8 VDD. So here VDS is going on increasing. So from 0 onwards, and VDS in depletion mode is going to be decreasing mode, right? In enhancement mode, VDS is going to be increases from it means so here enhancement mode device comes from enhanced mode into depletion mode, and the depletion mode device is decreasing their levels from depletion mode to enhancement mode device, right? So this is for the enhancement device, the enhancement mode device here. For VGS enhancement mode 0.2 VDD, the current will be like this. IDS is like this. For 0.4 like this, 0.45 like this, 0.8 like this. But VDS is here decreasing level from 0.5, then current will be going like this. So this is the point here where the cross section point occurs. Those are nothing but transfer characteristics of this Nmos inverter, right? So here by input, here V input is 0, here, okay, output is 1. Why? Because it is off condition. It is always depletion mode is here. It is depletion mode means it is in pull up condition. It is pull down condition. So even it is pull down condition, again you can apply the 0 volts here. Again it is in pull down means it is in off condition. So there is no way the current flows from VDD to VSS. Okay, VDD to VSS. Then output is high here. Output is high. That is VDD. That is equal to VDD here. So let us observe here. If you are applying 0 as input voltage, we are getting output is VDD. Logic high. Nothing but it is the inverter operation. Suppose so this V input is logic 1. Then this enhancement device going to on condition. So now there is a path in between VDD and VSS, or whatever the output response is available here, that will be discharged to ground through this device, through this transistor. So finally we are getting output response is 0 volts. Okay, let us observe here. Here input is 1, output is 0. Okay, it performs the inverter operation. So here from 0 onwards, it was going to slowly increases. Initially, it is occupies very high resistance. It is in resistive modes. Okay, means on condition. On condition means it occupies very less amount of resistance in terms of ohms. It is pull down. It is initially off condition means it is in terms of mega ohms. Whereas 0 volt from 0 volts to increasing order, then this conducting properties going to be increases and it is going to be decreases when the maximum value reaches to the enhance across this enhancement mode device. So this conducting property will going to be increases, this conducting property will going to be decreases. So means it is in saturation mode, it is in resistive mode. So in saturation mode means it is in on condition. So it occupies very less amount of resistance. And also here we say it is in resistive mode, right? And let us come to this point here. So by the conditions of inverter operation, whereas input is 0, output is going to be 1. Input is 1, output is going to be 0. But input is going to be increasing slightly from 0 to logic towards logic 1. Then how the performance of the transistors are going to be working, that is depletion mode, and that is nothing but pull up mode and pull down mode. So based on that, this is the curve formation here. So this is the depletion mode curve, depletion mode transistor curve here, and this is the enhancement mode transistor curve, where the intersection point, cross section point is occur, nothing but it is the transfer characteristics, right? So the point of intersection of this curve figure A here it is give points on the transfer characteristics, which from this figure for next figure I will show you. Note that so V input is, that is VGS, pull down transistor exceed the pull down threshold voltage, the current begins to flow. Okay, the input voltage is exceeding the threshold level of pull down transistor. nothing but VGS is greater than or equal to VT, then only we are expecting the pull down transistor going to be on condition. At that case, there is a path in between VDD and VSS, then current will be flow. Then the current begins to flow, right? Okay. Next diagram. So here, the output voltage, this is the transfer characteristics here. So let us see here, V input is 0, V out is high. V input is 0, V out is high. Suppose V input is going in increasing order, that is VDD, then output is 0. Okay, maximum it is 0. V input is VDD, output is 0. Okay, like this. If input is 0, output is high. So by increasing this V input, the output will be slowly decreases. The current will be going to be flow. Means the output response is decreases. Or the current will be flow because of by increasing this input voltage. Pull up device, pull down device are both are in a certain point. Both are going to be in on condition. So then the output response slowly decreases. Finally, enhancement mode going to be pull up condition and depletion mode is going to be pull down condition. Then the output response is completely 0, right? But practically there is a slight amount of voltage available across this device. Okay, so let us observe here. Initially, input is 0. So V out, V in response is like this. So Z pull up by pull down ratio is going to be increases. Z pull up by pull down ratio is going to be increases like this, right? Pull up by pull down ratio. Similarly, whereas input response is going to be increases, so this is going to be Z pull up by pull down ratio is going to be increase here. So where these 2 points, okay, so V inversion point, V inverter, V input, V output, that is nothing but transfer characteristics. Let us see this point here. So V output equal to V input, that is equal to V inverter. V output equal to V input equal to V inverse, nothing but this is the transfer characteristics, right? That is at 0.5. So at this case, the current will be flows, right? Right. Next point. During this transition, the slope of the transfer characteristic determine the gain. That is the slope of this transfer characteristics. Find out the gain here. Already you know that gain is nothing but output response by input response. That is change in output voltage by change in input voltage. Nothing but gain of the transistor, right? Gain of the inverter. The point at which V out, V input is denoted as V inputs, right? The point at which V output is equal to V input is denoted as V inverse, and it will be noted that the transfer characteristics and V inverse can be shifted by variation of the ratio of pull up to pull down ratio.